In this video, you will learn about inverse functions. Now, what is an inverse function? Well, the function f is the inverse of g if each ordered pair in f has reverse coordinates of an ordered pair in g. What that means is, for example, let's say we have our function f right here, which is a set of ordered pairs. So each x is paired with only one y value. While the inverse is seen right here in g, where we switch each x and y value. So instead of 2, -4, we switch it to get -4, 2, right here. Instead of 7, 2, we switch it to get 2 and 7. Instead of 1 and 6, we switch it to get 6 and 1. Instead of -5 and 4, we switch it to get 4 and -5. So we can say that f and g are inverse functions of each other. Now, another thing with inverse functions is we need to understand what is one-to-one. So what does this mean? So one-to-one means that the function f is one-to-one if and only if f of a equals f of b implies that a equals b. Now, the way we can understand this is we can realize that f of a, in this notation, a is the x value, and then f of a, that's like your y value. So that's the point a, y. And then f of b, b is the x value, and then we'll call f of b y as well. And it's saying that the only way for, or if f of a and f of b is equal, the only way for that to be true, where the y values are the same, is if a and b are equal. So implying that the y value can be paired with only one x value. A and b have to be the same thing. It can't be two different numbers. So the definition I like to use for one-to-one functions is that a function is one-to-one if each x value is paired with only one y value and each y value is paired with only one x value. So that's the definition I like to use. So because a function, to be a function, each x value must be paired with only one y value. That's where that part comes from. But then the one-to-one part is the other way around. Each y value must be paired with only one x value. All right, and then a way we can determine this, if you're given a graph, is we can use what is called the horizontal line test. So it's basically just like the vertical line test to determine if something is a function, but instead of a vertical line, it is a horizontal line. So we can determine if a function is one-to-one if every horizontal line intersects the graph only once. So for example, let's say we have this function right here. This is a quadratic function. It's a parabola. So it's a function because it passes the vertical line test. But it's not one-to-one because if you were to create a horizontal line, it's hitting more than one point at a time. So that makes it not one-to-one. And we know that to be true because if we look at this, this function, let's say it's y equals x squared, and we plugged in the number -1 for x. If you plug in -1 in place of x, we would have -1 squared, or 1 for y. But you can also plug in a 1 for x and get 1 back out for y, because 1 squared is also 1. So notice that this y value of 1 is paired with a -1 and a +1. So because the y value is paired with more than one x value, that means that this function is not one-to-one. And again, we verified that with the horizontal line test. So how does one-to-one have anything to do with an inverse? All right, well, a function has an inverse function if and only if it is one-to-one. So if it's not one-to-one, it does not have an inverse function. And also, another thing is if a function is increasing or decreasing, then it has an inverse function, which makes sense because if it's increasing, that means it just keeps going up. So it could be something like this. It doesn't have to be a straight line, but something that's increasing. We know that that's got to be one-to-one because it's passing the horizontal line test. And for that reason, because it's one-to-one, that means it has an inverse function. Same thing with a decreasing function, something like this, going down in this direction. This also is one-to-one because if you draw a horizontal line, it's only hitting one point at a time. And for that reason, we know that it has an inverse function. So if it changes directions though, so something, instead of going up all the time, but it changes direction, that would make it not one-to-one, and thus not having an inverse because it does not pass the horizontal line test. And then the notation for representing an inverse function is we use a little -1, so something like this here. So the inverse of f would be f with a -1 written above it. The -1 is not an exponent. Okay, it's not, doesn't mean raise f to the negative first power, but it is a superscript. It is written above like an exponent would be written, but it does not mean raised to the negative first power. Now also with inverse functions, we're going to talk about how to graph. So let's say we have this line right here, and we were told to graph the inverse of this function. What we can do is we can find a point on this line. Let's pick this one right here. It's at -3, 0. Now remember we said at the beginning, an inverse function is where you can switch the x and the y value. So that would give you instead 0, -3, which would be a point on the inverse of the function. And then let's find another point on the line. Let's pick this other intercept right here. It's at 0, 2. Now the inverse of that would be switching the x and the y value to get 2, 0. And you can put 2, 0 right here. So with the line, all you need is 2 points. So you connect those points, and now we have this new line. So this new line is the inverse of the initial function. So if this were f of x, this would be f inverse of x. And then something to take note is that if you were to graph the line y equals x, notice right here we have this line, and it's right down the middle in between the function and its inverse. And that's always going to be true with the function and its inverse, is that the function and the inverse would be reflections across that line. All right, so it doesn't matter what the graph looks like, it's going to be reflected across that line. Now another thing with these two functions, f of x and f inverse of x, is that there's a relationship between them when it comes to the composition of the functions. So we'll explain what that means when you say a composition of functions. But let's say we have a function f of x, and let's say f of x equals 2x minus 4. And let's say we have another function, g of x equals 1/2 x plus 2. So if we have these two functions, let's first explain function notation quickly. So you probably have learned this in the past, but we'll do a quick review here. So remember, if you have f of, let's say, 3, what that means is we put a 3 in place of x in the f function. So we have 2 times 3 minus 4, which would be 2. All right, do the same thing for g of x. We can do maybe g of 8. You plug a 8 in for x, so we have 1/2 times 8 plus 2. That would be 4 plus 2, or 6. Now, a composition of functions would be a function inside of a function. So let's say we had f of g of, let's do 4. So what that means is we start with the innermost function right here. We find g of 4. So g of 4, we plug a 4 in place of x. We have 1/2 times 4, which is 2. 2 plus 2 is 4. So g of 4 is actually 4 as well. So now instead of f of g of 4, we have f of 4. And then f of 4 we can find by plugging a 4 in place of x over here in the f function. 2 times 4 minus 4 would be 4. It's a lot of 4's in that one. So that's how composition of functions work. And instead of f of g of 4 written in that manner, I could have written that like this, with f of g of 4, with like a little raised circle in between the f and the g. that means the same thing as f of g of 4, like that. So that was just a little quick review of functions and composition of functions. But here with inverses, if we were to take a function and compose it with its inverse, so f composed with f inverse of x, that will equal x. So that will always equal x. And also, if you do the other way around, where you have the inverse of f composed with f, then that will also equal x. So both of these will always equal x, and we can also take the converse of that, where if both of these are equal to x, so if we take a function and another function, we compose them in both directions, and they both equal x, then we can verify that the functions are inverses of each other. So let's try an example here. Here we have f of x equals 2x minus 4, and the inverse of f of x equals 1/2 x plus 2. All right, well, if you compose them, so you take the composition of those two functions, let's see what we get. So we take the inverse of f of x, which is the 1/2 x plus 2, you plug it in there, so we have, now we have f of 1/2 x plus 2. And then what that means is in place of x in the f function, so right here, in place of x, we can plug in 1/2 x plus 2. So now we have 2 times the 1/2 x plus 2, and the minus 4 at the end. So if you work through this, you can distribute. We would have 1x plus 4 minus 4, and 4 minus 4 would give you x. And the other way around would also be true. If you compose the inverse with f of x, you put f of x here, so in place of that, put in 2x minus 4. So now we have f inverse of 2x minus 4. And what that means is we plug in 2x minus 4 in place of x right here in the f inverse function. So now we have 1/2 times, parentheses, 2x minus 4, and then plus 2. We can then distribute. We would have 1x minus 2 plus 2, and then the negative 2 plus 2 cancel, and you have x. So notice both the compositions would equal x when you do it both directions. And again, that could be a test. If you didn't know that was the inverse, if you were given this to be just g of x, and you were trying to determine if those are inverses or not, you would take the composition in both directions. So you do f of g of x, and you do g of f of x. And when you see that they both have x as the outcome, we have proven that those functions are inverse functions. Now in this example, we were given two functions, and we can determine if they are inverses or not. But how do you find an inverse of a function? Well, what we can do is to find the inverse, we substitute y for f of x, because those are interchangeable, and then you switch x and y. So that when you switch x and y, you then solve for y in terms of x. And then at the end, in place of the y, you put in the inverse function notation. Now let's walk through an example where we go through these steps. And here we have f of x equals 2x minus 8. So we're trying to find the inverse of this function. Now step 1 was replace f of x with y. So we have y equals 2x minus 8. Step 2 is we switch x and y. So instead of y equals 2x minus 8, we now have x equals 2y minus 8. And then to finish off, step 3 is we want to solve this for y. So we can add 8 to both sides to bring the negative 8 over. So now we have 2y equals x plus 8. And then get y by itself by dividing everything by 2. That would give you 1/2 x plus 4 equals y. And then your final step is replace this y with the inverse function notation, which is f inverse of x right here. So the inverse is going to be right here. And if we wanted to, we can verify that by finding the composition of f of x and f inverse of x, do it both directions, and you're going to find that it will equal x. And the other way we could do it, even to verify, is we can graph the line 2x minus 8, then we can graph the inverse 1/2 x plus 4, and it should be reflected, a reflection of each other, across the line of y equals x. Let's try another example. Here we have g of x equals x over 3x minus 1. So how do you find the inverse of this function? Well, again, we can replace g of x with y. And then from here, we can switch x and y. So now we'd have x equals y over 3y minus 1. All right, this one's a little trickier because we have two different y's, one in the numerator, one in the denominator. What we want to do is get rid of the 3y minus 1 on the bottom by multiplying both sides by 3y minus 1. When you do that on the right, they cancel. And then on the left, you have x times 3y minus 1. When you multiply x times 3y minus 1, you have to distribute. We get 3xy minus x, which is what we see right here. And on the right side, we have y. So the goal was to solve for y. So we need to bring y together. So let's bring, we can bring the y over here by subtracting, and bring negative x over here by adding. So when you do that, we'd have 3xy minus y equals positive x. And then over on the left side, notice they both have a y in common. So I can factor a y out. You're left with 3x minus 1 in parentheses, and then divide both sides by 3x minus 1. And now what you're left with is y equals x over 3x minus 1. And then to finish off, we can replace this y with your inverse function notation. And that would be the f inverse of x. So this is the inverse of the function, and actually, sorry, it was g of x, so that should be g inverse of x. Now, what if you're trying to find the inverse of a function with a restricted domain? So for example, you were told to find the inverse of f of x, where the domain is x is greater than or equal to -1. Well, we can go through the whole process of finding the inverse like normal. So we'll do that at this time. So we need to switch x and y. So you have x equals y squared plus 2y plus 1. And then we have to solve for y. And actually this works pretty nicely because this right side is a perfect square trinomial. So we can factor that to get, actually skip this line, factor that to get x equals y plus 1 squared. Which, by the way, if it's not a perfect square trinomial, you have to make it into a perfect square trinomial. So you may have to add something to both sides to make this work. All right, but here we have y plus 1 squared. And then we can take the square root of both sides. So if you take the square root of both sides, you're going to have plus or minus the square root of x equals y plus 1. And then you subtract 1 over to get y equals -1 plus or minus the square root of x, or you can write it the other way, plus or minus square root of x minus 1. All right, so that would be the inverse of the function, and we can replace the y with the inverse function notation of f inverse of x. But what we're trying to focus on here is what do we do with this restriction on the domain? Well, the domain of the function is going to be the range of the inverse of the function. So that's how that works, because they're inverses. So it's going to be the opposite. All right, so the range of this inverse function is y must be greater than or equal to -1. So for that to be true, when you have a plus or minus the square root of a number over here, we're going to only want the positive ones. All right, because if you plug in or take the negative square root of something, let's say this, you have -3. Well, -3 minus 1 is -4, and that's going to be smaller than -1, but you want something bigger than -1. So what that means is that we only want the positive answer, the positive square root, so we can just write that as the square root of x minus 1. Now to finish off this lesson, let's talk about an application of inverse functions. Now there's all sorts of different ways we can apply this, but one example is here, where we have 3 right circular cones with the same height, h equals 50 centimeters, that are to be constructed. The volumes of these cones are to be 200, 400, and 800 cubic centimeters. And we define the radius of the base of each cone. Well, for this one, we're dealing with cones and volume. All right, so we need to know, first of all, the volume formula for a cone, and that is 1/3 times the area of the base, which is pi r squared, and then times the height. All right, and we're told with this that all these cones have the same height of 50 centimeters. So we can plug a 50 in place of the height. So what this function is doing is it is letting us plug in something for the radius. So we're going to plug in something for the radius, and the output, what we're going to get out is going to be the volume. All right, but what we want is we want to find the radius given the volume. So if we find the inverse, so the inverse of this function will take the volume and give you back out the radius, which is what we want, right? Because we want to plug in these volumes of 200, 400, and 800 to figure out the radius of those cones. So this is an application of the inverse. We can take the inverse of this function, v of r, and that will help us have a new function that will give us the volume, or give us the radius when you plug in the volumes. All right, so one thing we can do is we can combine the 1/3 and the 50. So 1/3 times 50 would be 50 over 3. So we have 50 over 3 times the pi times radius squared. So we have that on the right side. On the left side, we can replace the v of r with the letter y. And to find the inverse, we're going to switch the variables. So in this case, instead of x and y, we have y and r. So you switch those to get r equals 50 over 3 times pi times y squared. All right, and then from here, we need to solve for y. So we need to get rid of the 50 over 3 and the pi and the squared. Well, to get rid of 50 over 3, we can multiply both sides by 3 over 50. So we have 3r over 50 equals, and then we have pi times y squared. And then to get rid of the pi, we divide both sides by pi. So divide by pi is multiplying by 1 over pi, which is going to put pi down here in the denominator. So we now have y squared equals 3r over 50 pi. And then, to solve for y, take the square root of both sides. Now we have y equals the square root of 3r over 50 pi. And we see that all typed up all the way to here. And then we can replace the y with the inverse function notation. So we can write v inverse of r equals that square root. So now we have this new function that, as we stated, we can plug in the radius, plug in the volume and get back out the radius. So I guess don't be deceived with the variable, because we did switch this around. All right, so this is just like a placeholder, kind of, it's a letter. But this letter has now been switched, right? So now this is your volume input. So that's maybe a little confusing, but we switched the variables, right? So because of that, this is now your volume variable. So we can now plug in the numbers 200, 400, and 800 to find the radii of those cones. So beginning with the 200, we do 3 times 200 over 50 times pi. You take the square root of that, and we're assuming you can type that into your calculator on your own, but your final answer would be 1.95 centimeters. And then do it again with the 400. We now have the square root of 3 times 400 divided by 50 pi. And again, type that into your calculator, and you get 2.76 centimeters. And then for the 800, you have the square root of 3 times 800 over 50 pi, and that would give you 3.91 centimeters. So notice once you have this formula rearranged with the inverse function, it is much quicker to solve for. So instead of having to solve an equation like 3 times, we solve it once and then just plug in the number 3 times. All right, so in this lesson, we learned about inverse functions and how to do many things with them. And that concludes our lesson for today. We will see you next time.